All righty. And hey, our goal was to be here by noon, and we're not too far off. Cool. And for those who were here last year, we didn't get to this point till about 4 o'clock, and those that were still conscious were indeed pretty crispy, and so we're, thank goodness, several hours ahead of that. So we are going to spend the rest of the day live tuning stuff, to where you're going to see in reality, and I'm going to tune stuff, we're going to go through the motions. And you're going to see the good, the bad, and the ugly of this process. When we get done with that, and hopefully we get that wrapped up by 4 o'clock or so, and then to the extent anybody wants to ask questions, how would you do this, how would you do that? Or we brought this year's comp bot. We actually had a pretty good season. It was a reasonably successful robot. And anybody that wants to know how we did any of those systems, happy to show you the mechanics over there and then take you through what we actually did. We won't tune it live. We've driven robots off tables one too many times. We don't power them up on tables anymore. But we'll try to get to the point where we can answer your questions or have a little bit of an impromptu whatever. So, who's ready to do some real tuning? Yeah, there was much rejoicing. Okay. A little bit about the tools. As you might imagine, you could tune this stuff this way. Well, I think it's about the right speed. I think it only overshot a little bit. No, my finger's on fire about the right time. It must be going about the right speed. That will work, but it's not very precise, and it will drive you crazy. Those of us who have been doing this for a while, you'd be surprised how good you can get actually doing it that way, but that doesn't come until you've made about 1 million mistakes and have all that experience. Tools to see what's going on inside here are unbelievably helpful. And unfortunately, there aren't really any good tools that are built for FIRST that are part of the FIRST program. You've got all the different languages and all the different stuff, but tuning tools, there's not really anything out there. Several teams have done some of their own stuff, and a couple of years ago we said, okay, we got to do something. And so actually the kid doing Program the Robot the previous 3 years, Alex, put a bunch of stuff together. He and I talked about what it needed to do, and we actually brought some tools to life. Turns out there were certain things that may have been hard-coded in there, and we were not very successful letting other people use those last year, and that was kind of a surprise to us too. We have rewritten those tools from scratch. The Grapper Tool is a LabVIEW-based tool to, in essence, give you a strip chart recorder to see what the heck is going on inside of the Talon. And it is intended, if you have a driver station that has LabVIEW runtime on it, that's what this uses. The platform it needs is the exact same platform your driver station needs. And if you have a driver station, which you probably have if you're at FIRST, this will run on that. Yes?
You actually don't need a driver station. The installer can download has it. So you can put it on anything.
Correct, and he is correct. The installer will do everything. So you could put this on any computer you want, and it will install the runtime on there. But if you've got something that's running the driver station, this will go right on that too. It uses the exact same lab. Yes, he's right. Separate computer too. So that is the Grapper. There is then a tool we call TCT, or Third Coast Telemetry. We're outsmarting ourselves. There's West Coast Drive and this stuff. There's East Coast stuff. But we decided to call some of the tools that we're doing Third Coast. We live on Lake Michigan. We call that a coast. So Third Coast Drive was what we called the whole swerve stuff. And this is Third Coast Telemetry. So you'll see me type in TCT. The TCT application is Java, not C. So this will run on a Java solution. And it runs in the RoboRio. And it is a command line thing to keep the overhead at a minimum in the RoboRio that lets you manipulate the physical things connected to a RoboRio. So I can say, Talon number 1, I want to do something with you. Bring that to me. Do this, that, and the other. Now run this speed. It gives you the ability to command line to manipulate any and all Talons. And you can do one Talon individually. You could say, these 4 Talons are my drive system. Group them together. I want to talk to them all at the same time. This is an excellent way to bring an axis to life, manually manipulating it and get yourself convinced my Talon, my motor, my encoder, and what's all going on in the real world is what needs to happen. So when the software folks try to turn it into something we can compete with, they go, oh, this is never going to work. You've designed this bad. It doesn't work. We say, oh, no, it works just fine. You don't know how to code. And the classic hardware-software battle, this stops right here because you can now separate all that and manipulate all that independently with a tool you know works. And so TCT does that. You can also drive DIO pins. You can drive the PWM. Anything you can drive with the regular software, you can drive with this, and you can also query with this. This gives you a tool set to manipulate and listen to anything you would normally be doing with the software. Okay? Very useful tool. And this year, Jeff's here. Jeff is head program guy for Stryke Force. He handled all the TCT stuff. We had some students involved, but little adult supervision this year. We're pretty sure this will actually install and run. And then Greg Rebeck, who's not here, and some kids worked on the Grapper. And the Grapper actually sits on a PC, and they talk through Ethernet to the Robo-Rio, and TCT, whatever you bring to life, it is offering that data up to the Grapper. The Grapper, you can then decide, this is what I actually want to graph, and then do graphing on all of that. So we won't turn this into a training course, but over in the Grapper, those screens are oriented way different than these two here. Over in the Grapper, I've got my control section. All the active Talons or anything I've actually talked to will show up in this list. When you click on that, everything you could watch shows up here, and then you shove that into this list of this is what I actually want to watch. And then when you go to the graph, all those items are here, and you can manipulate which axis I want them referenced to, what color I want the line to be. You can put dots on here too, where the dots are the actual data point. So you're not getting fooled by interpolation. What actual data points were coming out of the Talon? You can turn the dots on and the dots off. And lots of capability with colors and all kinds of stuff. So normally I've got an axis on here where you've got plus and minus 12 volts. You want to watch that quite often. The blue axis tends to be current, and I realize those in the back of the room probably can't read this. The blue axis is current right now. I think it's 0 to 60 amps. Velocity is on our green axis. That is sitting here at plus and minus 750. And then I've got a yellow axis that I think is, what, plus and minus 50, that I will use for my error. And you can actually, on the Talon, say, hey, that value right there, what is that? And we can plot that. So you have the ability with the Talon to say, I want to watch that point, I want to watch this point, I want to watch this point, I want to watch that point. You can graph all this stuff and see what's going on dynamically. Unbelievably helpful.
Can you get the individual PI and D terms out?
Yes, it doesn't graph them, but you can ask what they are.
Okay.
Yeah, TCT, you can go query a Talon and it will list out, this is the current value for everything.
Okay.
Which once again, when you look at how we normally do this at Stryke Force, there is a spreadsheet that got shrunk down a little bit. There's a spreadsheet for each axis, and we have got stuff over in this area where here this is motor RPM, your gear train, all your encoder stuff, everything that goes on, to where I can put a motor speed in and say, okay, I know this pull is at that speed, that's at that velocity, this is this tick rate, to help you keep track of what's going on. You literally build a little spreadsheet model of your system, and then over in the chart over here, these are all the different things in a Talon you have to worry about, and for any given mode of operation, what are those values? However you do it, keep track of this stuff. There are too many variables, and the moment something is programmed in a way that's not what you thought and you didn't even think you were programming it, you will pull your hair out. I've been doing this for a while, helping the kids with this stuff, and the other night at home I was working on something, and I inadvertently, not even knowing it, managed to get the minimum output of the Talon programmed at 12 volts. And I was overdoing some, actually I was firing up all the tuning from last year on all this because it's all done. And I'd fire up the motor and it would go crazy. I'm like, what on earth? Nothing changed, the tuning shouldn't have changed. And there's an interesting long sequence here, but I kid you not, 3 hours later, I finally figured out, oh geez, the minimum's at 12 volts, which means the Talon had one choice. Am I going too slow? 12 volts. And I'm going to be at 12 volts until I'm going too fast. Then I'm going to be minus 12 volts. Can't even get to zero. It had two outputs, plus 12 and minus 12. And with some of the other tuning, it was not obvious what was going on. Great case. I lit 3 hours on fire because of value that I didn't change. Ended up, I did change it not knowing. Keep track of all this stuff. And the moment things don't work as you expect, go read out all the values, write them down, and say, is this what I thought? That will get rid of 80% of your, this Talon's crazy, I can't make it work problems. Yep. All right. No. One of the beauties is it's persistent and you don't have to worry about it forgetting. One of the bad things is it's persistent. It doesn't forget. And you will actually note here on my cheat sheet for my script of going through the tuning, the first item on the list is set everything to 0, because as much as I might think they're 0, they won't be 0. In the middle of trying to teach you guys something, crazy stuff will happen. So you just go through and 0 it, or put in what you want it to be. Hence, have a spreadsheet, have every value. Even if you're not going to use it, know it's 0 and go put a 0 in there, because these things don't forget, including the one you took off the robot from last year. Yes?
Does TCT allow you to load the parameters from the file, so you can load them all at once?
Yes. TCT has the ability to save configurations as well as load them. And so once you get something figured out, you can say, save this configuration, and you fire TCT back up, you say, load this, and it will load it and say, okay, like on the drive system. I've got Talons 1 through 4, it's my drive system. This is all the mapping of all the values. Load my drive file, put all that in there so I can go work. That way you don't have to do all this from scratch every time. Yep?
So you're doing the loading first, and then running your code from your serial.
Well, keep in mind, TCT runs inside the RoboRio. And it's using the file system in there. It's inside that. And it is dumping data onto the Ethernet cable over to the Grapper, which is LabVIEW running on the PC. And the Grapper, then you choose, what do I want to watch? TCT is offering up, this is everything that's available. You tell me what you want to watch and I'll stream the data. And I believe, Jeff, it only streams what I'm watching. It doesn't burn bandwidth on everything. So, those are the tools that we use to keep track of what's going on. If you're going to do this PID stuff, you need something. You know, if you're just getting started trying to do this seat of the pants, you are probably not going to be successful. Okay? All right. So, let's dive right in. Now, conveniently, while I can see what's going on here, you guys probably can't. So we put a camera on that, and there are two systems here. We have a sim motor, a sim coder, which gets me 80 ticks per revolution, and a pulley on here that Mark colored this morning so you guys can see it spin. And it's interesting as well as hypnotic, so there's secret approach here. And that's straight out. That is simply on the output of a sim. So full speed, that'll run about 5,400 RPM. We then have a 550 motor driving 100-to-1 VEX gearbox stack. There's a couple of 10-to-1 planetaries going into one of their encoder stacks and then coming out to this big pulley that has got a white mark on it so you can see it. We're going to program this in position where you're going to see that mark go chink, chink, go different places. But that is a motor through a 100-to-1 gear train with the encoder stacked on the output of that. So my absolute encoder is 1-to-1 with my output here. So my absolute encoder straight up is always going to be the same value. So when I powered it up, I could say, okay, I need you to go to this value, and it would always go straight up. So those are the two platforms we're going to do. We're going to do some velocity work on the sim, and then we're going to do some position work over on the 550 and the VEX stack. So let's see if all this stuff works. And I may jump back and forth to several slides as we go if we need to reference something. And indeed, if there's something we do here that doesn't make sense, holler, and we will attempt to back up and get you there. The meat of this session is really what we're about to do. All right. So first order of business. Does my Talon actually run my motor? And does my motor go the direction I think it's going to go? And does my encoder give me a positive output when my motor goes positive? If your encoder gives you a negative output when your motor goes positive, it might be fun to watch you attempt to tune that, so others might find enjoyment in that, but you won't, because it's not going to go well. The phasing has to be right, or it will instantly oscillate. Okay? All right. So first thing I'm going to do is make sure all this stuff is programmed at 0. So I'm going to take a little look here, and I realize a lot of you may not be able to read what's on the screen. We tried to blow it up as big as we could. You just have to trust me. So let's see, I'm in voltage mode, which is good. My set point is 0. I do have some PID values in here. I think I want to 0 all of that. The absolute, my encoder register's got a really big number in it. And everything else looks good. And we'll talk about it in a minute. My velocity filtering is 164. And I've got a slide on that later. So that looks good. Let's look at my other data. And that's all okay for now. And so I am going to go 0 a bunch of stuff. I want my P to be 0. I want my I to be 0. I want my D to be 0. I want my F to be 0. I want my I zone to be 0. I want my allowable closed loop error to be 0. And we're not doing motion magic right now, so we don't care about that. Let's see, output limits and ramp rates. I want my ramp rate to be 0. I want it to be instant. And my peak output, we're going to use the full 12 volts. And these may already be set this way. I'm just being careful. I want my minimum to be 0. This thing needs to get to 0 when it get there. And let's see, for that, for current limit, I think we'll do 40 amps. And we're going to let this thing coast. Good. Okay. Big safety tip. When you're going to fire, and if you've got a motor on a system on a board, a SOB like this, pretty safe. It's not going to get away from you. On your robot, the first thing you should do is put a current limit on the motor. And I would start with a current limit that's really, really small. If something goes terribly wrong, it buys you time to figure out what went wrong and get it turned off before your motor catches on fire. A sim won't catch on fire instantly. I can blow smoke out of a 550 in 7 seconds. And so if you get it wrong, you have 7 seconds before that motor is trash and smells really, really bad. Putting a current limit on there, when you think about, okay, what job am I doing? Turn that current limit down, perhaps even more than what you need. You can always turn it up. It will save you until this thing is doing what it's supposed to do. On a position thing, put the switches on it and put hard limits on it and enable that in the Talon. Let the Talon save you from driving something into a solid wall or rotating something where it can't rotate and you tear up chains and gearboxes and whatever. All right, so I think I have this programmed up, and let's go check. I believe I'm in voltage mode. Yes, I'm in voltage mode, so cool. So on my list here, I can say, show me what's going on with the Talons, pick a Talon I want to work on. configure that Talon. There's another thing that shows me some data. Run the Talon, or load a Talon configuration, or save a Talon configuration. So I'm going to go actually run a Talon. And it says enter the voltage you want it to go, or hit enter with nothing, or B to backup. And in TCT, the letter B is always backup. So wherever you're at in the menu, if you hit a B, you back up the menu. So I'm going to say, all right, let's try 6 volts. Hey, bonus. Motor spinning over here. Excellent. It's actually spinning over there too. Now we are in voltage mode. So I've got 6 volts going to that motor.
Is the graph supposed to be changing, Jerry?
It will in a second. And I can slow that down, and I'm running up and down that speed torque curve. The graph's not running.
Okay.
Now, gee, it'd be nice if I had some data on that. So over here, I've told it, okay, this is all the stuff I could look at for Talon number 1 that is running that. I actually want to watch my set point, my output voltage, my output current, my encoder velocity, my control loop error, and my bucket on my integrator. How full is that bucket? That's a key thing to keep an eye on. So I'm going to watch all that stuff. And once again here, when you configure a given thing, you can load and save that as well, so you're not reconfiguring this every time from scratch. Come over to my graph. This is the picture. These are my scales. The color here shows you which axis that's being scaled to. The text in here shows you the instantaneous value. Now, a version of this we hit on this morning makes all that font white. It also breaks it so it won't work. So you're back to this version. So I realize you might not be able to see the values that are in there, but that's an instantaneous live value. Here you can configure the axes. There's lots of things you can do with the plots, all the colors, line style, blah, blah, blah. You can determine here which axis you want that plotted against. So lots of LabVIEW tools to make this however you want it. Down here is a speedometer telling you what is the data rate coming out of the Robo Rio. As I do more things, it slows down. And so when I turn this on, right now I'm running at about maybe 175 samples per second. So that is the rate at which I'm getting updated data on my screen. If I diminish some things, I can actually get this to run at 200, or in essence, a data point every 5 milliseconds. And when you're tuning something very specific, you actually need all of that. You need resolution down to 5 milliseconds to see what's going on. I also have the ability to manipulate a little bit what goes on with these axes. That at the moment's a little bit buggy, and if I touch it, this blows up. So just trust me, eventually that will manipulate these axes exactly like you want it. But I'm not going to touch it right now because bad things will happen. I can turn on and off my data streaming. I have a plus and minus to scroll the time scale on my x-axis. There is also a value that prints out here to actually tell you what scaling you're at in your x-axis. That's also in the version we took back off this morning because it doesn't work. So I would come over here and get this scrolling where I like the rate. And here, say, okay, I'm at 6 volts, commanded. It's actually outputting 5.99. Cool, that's what I told it to do. My current is at 1.12 amps. My encoder is running at 331 ticks per tenth of a millisecond. So if I was, and why not a second is a long story. That's a cross the road thing. So the encoder on here has 80 ticks per revolution. So I'm running some speed, and it's giving me some tick rate. That tick rate is actually 3,032 ticks per second, or 332 ticks per tenth of a second. So the internal velocity stuff in the Talon keeps track of all that in tenth of a second increments. So just know that if you use the native units, it's encoder ticks per tenth of a second. That's the value you're dealing in. You can always do the math and figure out, well, what RPM is that really? That's what we do in these spreadsheets. Like on here, if I punch in 5,400, That is 720 ticks per tenth of a millisecond. So we do all this work in the spreadsheet to get you all acclimated. We find that easier and less problematic than actually putting in the scaling and making this talk to me in RPM, because then I lose track of the resolution of my encoder. So we are sitting here, and no closed loop. My error is 0. It's supposed to be. My integrator is 0 because I don't have anything turned on. My set point, that's yellow, that is 6 volts. Bonus, it's supposed to be. My current is 1.12. Yep, that makes sense. We're on the blue axis. My velocity is green. That's at 334. Yep, I'm at 334. So everything seems to be working. So let's introduce a load. So what we see happen is when I load this, what I'm doing is that speed torque curve, and you can now think about the 6 volt line, because I'm only commanding it with 6 volts, and the Talon is open loop. It's doing 6 volts, period. As I squeeze that, my torque goes up, the motor slows down, my current goes up, and I'm coming up that speed torque curve. And in an effort to not light my fingers on crap. Too many windows, and you've got to be in the right one when you click the number. Okay, I'll slow it down a little bit. So at 4 volts, this thing will stall at about 12.5 amps. So if I were to go look at that chart, I'd probably find out that that motor at 4 volts, when you stall it, you're going to be at about 12 amps, and that's what it is. So I'm running it up and down that speed torque curve just by loading it. This is open loop voltage. So that all makes sense. And gee, question, is my encoder wired to go the right direction? I'm forward volts, and cool, my speed is forward. So as I go more forward, my encoder goes more positive. If I was to go negative.
And direction is simply the sign, right?
Yep, direction is the sign. I tell it minus 4 volts, and now output's minus 4 volts, and that thing is running the other direction. And so right here you see I'm at minus 200. Let's go back to 4 volts. And you can also stop the graph and scale, and you can expand and contract and look at things. And so what happened is I was at minus 4 volts. I told it go to positive 4 volts. That happened instantly. The Talon, actually, scale is that on? Oh, the reason you don't see the red line is because it is perfectly under the yellow line. The Talon immediately went to 4 volts, so it started applying the torque to the motor to go the other direction, but it took a moment. The motor had to slow down, reverse, and go the other direction, and now it's actually running the appropriate speed for 4 volts. So the motor can't change instantly because there's inertia in the rotor. But I'm pretty happy, and the moment I said go, the current came up as it did that event, and then my current went back down to next to nothing when I'm just sitting here idling. Okay. So, I'm pretty happy my physical plant is in good order. The voltage makes the motor do what it's supposed to do. Let's see what full speed is. Let's do 12 volts. Okay. 12 volts will run me about 710 ticks per tenth of a second. That's 12 volts. If I were to do minus 12 volts, that's pretty violent on the motor. Full speed one direction, full speed the other. And I'm 709 in reverse. So this motor is actually timed pretty well. The brush orientation, if it's not perfect, it'll run one speed forward and a different speed reverse. So don't panic if you see that. It's all about how perfectly symmetric the brushes are. You can also see that change over time as the brushes wear. All right, so that's all good. So we go back to 0. All right, I think I'm ready to close a loop. So let's put some P in this. And we did some of this training at Stryke Force, and there was always much amusement. Every time I talked about putting P in an encoder, there was laughter in the audience, because there are kids.
So
Yes?
I have a question. The feed forward is
I laugh
essentially
too.
to limit the initial area, right? Going into PID.
Yes.
So do you have a rule of thumb for where you set that relative to your set point?
Why, it's almost like I paid him to ask that question, which I didn't. Because I was about to say, hey, you know what? Before we set P, why don't we do the heavy lifting with F? Let's see how much we can get done with F. And so you're going to get your question answered right now. Indeed, we would want to set F before we set P. Now, F in essence is just scaling on voltage mode. Go this speed, multiply it by a number, output some voltage. But we're going to figure out what that value is. So let's see, let me back up here. We're going to go to speed mode and do speed. So now I am in speed mode, so I'm closed loop. I've told the Talon when I give you a value, and turns out I'm going to give it 300. We're going to kind of run the motor half speed to do a lot of this work. I'm going to give you 300, and when I hit go, you figure out how much the error is, run all the error through the math, and you make the motor run the speed it's supposed to run. So let's see what happens. Okay, good news is my set point changed to 300. Excellent. And what speed is my motor at? 0. What is my control loop error? 300. I got lots of error. If we go back here, I got lots of error. I have no RPM. Why not? Is what? Yep, not only is P 0, F is 0, I is 0, D is 0, and all that error times 0 is nothing. So, we got to put some values in there. So, what I'd like to do is dial my F up close enough so that this is almost the right speed. The set point for F, and once again, I am going to grossly oversimplify a lot of my guidance, but this will get you in the ballpark. Later when you take your college course on PID control, you can do the fine-tuning work. I'm going to dial F up until I get my value almost to the right place, and then I'm going to stop. If I actually went too far, PID would still fix it. PID would actually slow things down to make it go the right speed. But for lots of reasons, the right place to set F is a little bit below the set point. So,
What's a little bit?
Yeah, probably 5% below. And you can play around with a little bit. Honestly, where you do your ultimate fine-tuning on F, and it's because how this all stuff interacts, you start with it about there, perhaps 5% below. F will not be linear. If I run this at 600 RPM command, or 600 ticks command, I'll run some speed because I've only got F in there. As I slow down, that gap is going to increase because it's non-linear, and that's just it. There's no feedback. So we'll set F, and then we'll look at the range and see where we're at. All right. And so I could go through a bunch of math and figure out roughly where F needs to be. I'm just going to guess and see what happens. And if the motor runs full speed, F's too high. And if the motor doesn't move at all, F's really low. And if the motor runs something in between, okay, now I have a starting point, and I can go up and down and figure out where I need to be. So I've got 300 in here for my set point, so that's there, and my error is 300. I have error, so the moment I light F up, I should get something running out of this. So let's back up. I'm going to go configure this, and we're going to put a little F in. All righty, and I am going to start at 0.5. Why? That seemed like a good number.
What's the range of values?
0 to infinity. Actually, it's 0 to
16 or 32-bit number.
Unsigned integer, I think. So yeah, way bigger than you ever need. Big enough that the motor never stops. So I put 0.5 in there, and what's going on? My motor is indeed turning. Cool. And when I look now, 300 was my command. It's only going 80. My error is still 220. I can probably put some more P in this. Okay? I'm sorry, some more F in this. So let's put a little more in. And let's go crazy. Let's double it. Now we're at 1. Cool, closer. I've now got almost 200, but I've still got 100 of air. Okay, let's go more. We're going to go 1.25. As soon as I do this right. Oh, looking pretty good here. Okay, so I told it to go 300. I've got F to where it's going 260. Not too bad. I think we'll sneak up on it just a little bit more. Let's do 1.35. Oh, okay. So now 284, I've only got an error of 16. Yeah, I don't want to go any more than that. That's certainly inside of my 5% window and not over. All right, cool. I told it to go 300. It's almost going 300. Let's find out how consistent that is across my RPM range. So let's do 500. Yep, 504, a little bit over. So maybe I got F just a little bit high. 400 goes 395. 300 is 285. 200 is 176. Now you will notice as I'm slowing down, I'm going from a little bit too much F to not quite enough F. It is not linear depending on the motor and lots of stuff, because in essence, it's just what is my speed times my voltage. I have no idea what's actually going on with the motor. And this is going to get worse as I slow it down. At 100, now I'm going 68. So now I'm only going 68%. At 50, this is going to be a train wreck. Okay, at 50, I'm going 17 RPM. So at these low speeds, this really falls apart. And what you will find is volts versus speed. In 10% of motor speed to 100% of motor speed, it's kind of linear. The bottom end goes way nonlinear. And so you would expect F to not get the job done when you're programming motors very, very slowly. And so if I go back to 500, I'm at 505, and I'm actually okay with that. I know you told you never program it over, but with some experience, you can do it a little bit at one end of the scale. What I really care about is most of the time, I'm a little bit under. So at 300, which is kind of middle of the road, remember 710 was full speed, 710 is 5,400 RPM on this. That's middle of the road. We're going to do a lot of our tuning kind of middle of the road. Yes?
If you had a mechanism that you had a small set of speeds that you wanted to run it at,
Yep.
that's where you would use
Correct.
the profiles.
Correct. Yep. First of all, no need to tune it outside of where you're going to use it. And if within that range, you needed it to be so optimized that one set of values worked here but not here, this is where you use those slots in the Talon, and you can use the Robo Rio to watch the speed and change the tuning on the fly. We do that quite a bit when we're using wide dynamic range on something. All right, so I'm going to put F at 1.35 and say that does most of the heavy lifting. That gets me pretty close to being the right speed. Say, all right, cool, that's good. I've gone through my dynamic range. It's not awful. We're going to leave that there. And now we're going to go try to do a little bit of P. All right. So, what value should I start with for P? Nobody's got the courage to guess because they're pretty sure there's some catch here and I'm going to have fun at their expense.
47.3.
Wrong. We could do that, and then this is going to run full speed. If we were to go through the math and say, okay, I know my set point, I know my error, I can do the math, I know 1024 gets me 12 volts, I can actually figure it out, you very quickly will get a sense of, okay, with an encoder of this type of encoder, I'm going to start roughly here. And you'll go from there. What you want to do is to get it to where you're somewhere in a linear range, where if you change it, it changes, and then you can tune from there. You don't want it to go 100%, you don't want it to go 0, because that doesn't tell you anything. The other thing to know, in the Talon, the speeds are not normalized. The encoder ticks are the encoder ticks, and the math is absolute. If I told it to go 300, and it's going 290, I have an error of 10. Let's say I have an encoder on here that runs at 10x that rate. I get 3,000 ticks per tenth of a second at that same speed. Okay, pretty quick study. I'll put 3,000 in here, and it'll go the right speed. Now, if I'm off that same amount, before I used to have an error of 10. But I've scaled up my encoder by 10 to 1. I've now got 3,000 or 10 ticks for every single tick I used to have. Not a problem, I'll just crank my math up, but my error goes up by that same scale, even though my motor is at the same error RPM-wise. This math is absolute, and so if I didn't change my proportional value by a factor of 10 too, I've changed my tuning by changing the encoder. So when your encoder has a higher tick rate, your values have to be lower to get you the same output coming out of here. If I were to put one of the cross-the-road encoders on here that has 4,000 ticks per turn instead of 80, we'd be starting out with P way, way, way lower by that exact ratio, so that that same error times that P value gets me my same result. So just think about it. As your encoder rates change, your P values change. In the normal real world, there's always factors that normalize this so that your P values don't change. The tuning is tuning. Here, we're adjusting for that by actually changing the values. This is 80 ticks per, and I'm actually going to start with a P value of 0.1. How do I know that? Because we've done this a lot and it's experience. So 0.1, and I'm about to hit enter, and what you should watch, I'm running 300, I have an error of 15 based on my feed forward, but I'm about to put some P in here where that 15 times that value of 0.1 is going to add something to this, add to that, and my output's going to go up a little bit. Let's find out how much. And so we're at 15, here we go. Cool. We got it down to 13. Who's excited about that? All right, they're excited something happened, but we can probably do better. That's still a pretty big hit. The good news is we saw an effect and nothing went crazy. Kind of what we hoped would happen did happen. So let's see. Let's double. A lot of times when you're tuning at the gross level, you double the value and see what happens. So I'm going to go to 0.2. And I didn't do that right. What did I actually change? And my air goes. Now the motor's heating up a little bit, not much. And let's go to 0.4. Ah, now I'm down to 12. So I keep cranking up my proportional gain, and it's eating into that air. I'm not going to get it to 0, but I'm eating into that air. So we're going to keep going. How do I know when I've gone too far? It oscillates. And it's back to, if I put too much gain in it, I'm now all over the line. What might be an indication that there's already maybe a little bit of oscillation going on? See my air bouncing back and forth? Might already be a little bit going on. Also, though, when I look at it, That's plus or minus a single digit. That could also just be noise bouncing between two values. So we're going to do P, where am I at? 0.4. Let's do point. Let's go crazy. We're going to go to 1. And 1. My error is down to 8 out of 300. Not bad. I'm now at 92% the correct speed. And things look stable. My error is bouncing between 9 and 8. That could be the beginning of some oscillation. Could just be bouncing between two values. Don't really know. And so let's do more. Here's 2. When you look at my green velocity line, are you starting to see a pattern there? Yeah, I'm probably getting pretty close to making this thing oscillate. Here's another good test. Let's do a gross step response. Oh, yeah. If I knock it off the line and it tries to get back onto the line, yeah, it's not pretty. So P is too high. If I kept going, eventually it wouldn't need me to do that. It would just take off. Yes?
The orange line is
The error.
Yeah.
Now,
Jerry, your scale doesn't match the line. You said green, that's why.
oh, sorry. The another little trick that's helpful. The green is my velocity, and indeed that ringing is happening on that green line. The error is mathematically also how far is my green line off of my set point. It's hard to see because of the scaling on the green line. My error, I have that scaled around 0. Lots of gain on that. So I, in essence, have blown up. The variance on the green line is huge on my error line, so it's much easier to see what's going on watching the error.
So
Yes.
both
Would it be possible to use those extra decimal places in order to cut down on that noise you really low, what might be the start of the beginnings of oscillation?
Potentially, yeah. Now here, as it turns out, we were in the mud. The encoder, this has only got 80 ticks per revolution. And so we were bouncing around 2 numbers, that's all there is. We're in native units, there is no subunit. If I put a high resolution encoder on it, I'd have a lot more data, then I could do exactly that. All right, so we have seen that we've gone too far, because this is a big old party.
Jerry,
Yes?
just for kicks and giggles, could you just push it way too far?
All right, let's go crazy. No, not 14. Whoop. Okay, I just screwed up. Hang on. And there is 4. Also, look at what's going on with my current. My current is running between 2.5 and 30 amps. And so, if I'm saying, Coach, mentor, what's going on? This is crazy. I don't understand. Meanwhile, a small fire is started. And that is actually what is going on right now because there's 30 amps going into that thing because all that energy is speeding up and slowing down the motor. So let's do something about that. All right. So even though it's not like this thing sounded like it was going 900 miles an hour, it is using 30 amps to accelerate it faster and 30 amps to accelerate it slower. And the copper doesn't care why. The copper's getting hot. And what is 1 amp squared? Well, that's 1. What is 30 squared? 900. There's 900 times more heat going into this thing when it was doing that versus this. Start your stopwatch before that thing catches on fire. Hence, oscillation can consume an unbelievable amount of energy because it is speeding up and slowing down your mechanism very rapidly. All right, so there you go. 4 is way over the edge. Now, I'm back at 1. Looks stable. Let's do the glove test. It stabilizes, but I overshoot and I ring a little bit. I'm okay if it overshoots and settles. I really don't want it to overshoot and undershoot and ring. So I'm going to take a little bit more out of it. So we're going to go back to 0.5. Okay? So we're now at 0.5. Okay? Let me do this and look at this stop. Okay, and so now I introduce the event, it recovers, I overshoot a little bit, and I can see here's 0. My error comes down, and then it settles very quickly. And my error is simply the math of how far this green line is away from 300. It just is a lot easier to see. See how much bigger this signal is than that green signal? When you get to fine tuning, you can amplify your error a lot, but you can't amplify the green line because it goes off the screen. So the error line is a great thing to watch to see what's going on. And I'm actually pretty happy with that. That's okay. That's probably a good place to leave P. If I made P less, I wouldn't correct as much error. If I made P more, it's a little bit too unstable and that'll come back to haunt you. So I'm going to call that is good with P. If you look at the cheat sheet at the end of this, it basically says turn up P until it oscillates and then cut it in half. That'll get you close. And in this particular case, 2 was pretty close to oscillating. Probably 3 would have actually oscillated. That would have told us 1.5. It would be stable, but when we grab this, you'd see it overshoot a little bit, say, I want to take a little more out of it. You're about right when it overshoots kind of one time and then settles. That's a good starting point as you're going through this the first time. So now I've got F set to do most of the heavy lifting. I've got P set about as high as I can get it to correct some of the error, and it corrects it in a hurry. The integrator packed a lunch. But with P, it's instant correcting that error. So, okay, I've now got F and P set. So, but what do I got for error? Turn my grapher back on. I got 11. And you know what? If 290 is okay, I may be done. You know, it recovers pretty fast, it's stable. If I don't really care that much, I might be done. And you will notice. Watch my volts right here, my 5.16 volts. If this was just only F, that voltage is not going to change as I load this. As I load this, you're going to see that voltage go up a little bit. You watch the red line, it goes up. That is the math out of the green box being added that summer, actually cranking up the output. So you are seeing that feedback do something when I slow this down. All right.